Hey, we're going to do Hess's Law, so that's 5.2 in your textbook. The textbook does a pretty good job. There's two ways to do Hess's Law. I'm going to show you one way, which is my favorite way, but the textbook also describes what's called cycles for energy cycles, and maybe we can talk about that next time I see you in class. So Hess's Law really is just a tool or kind of a reaction way to describe a reaction, I guess, and for things that are hard to measure. So let's say that you have some reaction that you cannot physically do in your laboratory, or there's something that's holding you back from doing it. Maybe you don't have the materials or something. You can predict what the enthalpy change will be based on other known reactions that we've already studied. So you can calculate a reaction's enthalpy change based on known enthalpies of other reactions, and you can combine multiple reactions. Now, before we get into an actual example of this, I'll give you a couple of notes on that. If a reaction is reversed, your enthalpy value, so your change in enthalpy, is also reversed. So here we see that with nitrogen and oxygen gases reacting to make nitrous oxide. And as we flip that, so it's in the opposite direction, it takes the opposite sign here. So it goes from 180 kilojoules to negative 180 kilojoules. So that's important. Every time that you flip it, you will need to change the total enthalpy number. And finally, if the coefficients of the reaction are multiplied by an integer, you have to multiply that by the same. So from the example above where you see 2 nitrous oxide, we multiplied that whole set by 3. So you see that there's 6 nitrous oxide, 3 nitrogen gases, 3 oxygen gases. And as a result, we had to multiply our initial enthalpy change of 180 kilojoules by 3. So I'm going to go through an example here just to show you guys like how we try to process these. So this is a couple of examples from the worksheet that I'm going to get you guys to work on. Now, what we need to do is we need to make sure that we are looking specifically for this reaction right here. So we're going to want carbon on the left-hand side, we want oxygen on the left-hand side, and we want CO2 on the right. We also want them to have the right number of coefficients, and we need to use these values in order to figure out what our total enthalpy change is. So first, I look at my first reaction. I usually like to label these 1 and 2, just so that way you can kind of keep track. So I'd say copper plus 1/2 O2 makes CO. Now, I know for sure that copper's in the right spot, so I'm okay with that right now. And carbon monoxide isn't even in the equation itself, so it's not in the final reaction. So that's something I need to cancel. Now I look at my equation number 2, and I'll write that down as carbon monoxide plus 1/2 O2 gives me CO2. Now, when we have something on one side, like carbon monoxide, that is, we have the same thing on the other side, we can cancel those out and say that they are no longer part of this reaction. As a result, we'll actually collect all of these terms and we'll add everything together. So that way, this carbon, we'll say that we still have 1 carbon as a solid, of course, plus we have 1/2 oxygen plus 1/2 oxygen gives me 1 whole oxygen gas, so that's going to be oxygen gas. Will give me, and because my CO, my carbon monoxide, is canceled out, I'm left only with CO2 gas on the right-hand side. Now, I didn't do any flipping and I didn't really change anything, so my delta H value for the first reaction is negative 110.5 kilojoules. For the second reaction, it's negative 283.0 kilojoules. So as we collect those and add them up, we should get 0.5, that's going to be 3, 9, and 3, right? So basic math is having a hard time figuring this one out today, but there we go. So that is the new enthalpy value for this reaction. So we figured out that this reaction, the formation of carbon dioxide by carbon and oxygen, has a negative 393 kilojoule enthalpy change. Another example here with question number 2. looking at a different way to manipulate. So I know that I have xenon plus fluorine gas. It's going to give me xenon fluoride, F2 as a solid. Delta H is equal to negative 123 kilojoules. And my second reaction plus 2F2 gives me xenon tetrafluoride. And my enthalpy of reaction is negative 262 kilojoules. So here we need to make sure that our xenon difluoride has to be on the left, right? So this has to be on the left. So I'm looking at moving that over to the left-hand side. My F2, I have to have a fluorine gas, and on the right is xenon tetrafluoride. So tetrafluoride is already in the right spot, so we are good with that. Now, in order for us to get our F2, our xenon F2, so our difluoride, to the left-hand side, we're going to have to flip the equation. So I'm going to cross this out, and I'll write down a new equation down below. Xenon F2 is going to yield, right? So I flipped it. It's going to yield xenon plus fluorine gas by itself. Now my enthalpy value here changed from negative 123 kilojoules to positive 123 kilojoules. That's really important in order for this to be correct. So make sure you're following along with your signs, and if you flip something, you need to flip your sign as well. Okay, so here we have a xenon on the left side and a xenon difluoride on the left. So the difluoride is good to go, but we need to make sure that these xenons themselves will cancel out. So there's one of them on each side. Now, here's where it's interesting. There is one F2 on the right, so we'll cancel one of those out. Now, the ability here for these two F2s to cancel out, there's only one that can do that. So because there's one over here and there's two over here, only one of them will be canceled, and now we'll be left with one. That was a little bit confusing. You can come in and see me in class. We can sort that out. So, and the result is going to be xenon difluoride plus fluorine gas will give xenon F4. And I'm without a calculator right now, but let's do this again. So this will result with an enthalpy change of negative 262 plus 123. You can do that for yourself. I've never been a mental math magician. There we go.